Hello, students, and a very warm welcome to you all. Today, we're going to dive into a fascinating topic from our gravitation chapter, something called free fall and the acceleration due to gravity. You see this happen all around you, every single day. But have you ever really stopped to think about the physics behind it? Well, today we will. So, what's on the agenda for today? Let's have a quick look. We'll start with a very simple question. Then we'll get into what exactly freefall means. After that, we'll meet its very important partner, the acceleration of gravity, which we call g. We'll even figure out how we get that famous number for g. And we'll solve a common puzzle about why different objects seem to fall differently. And finally, we will wrap it all up with the most important points to remember. All right, let's begin. We're going to start with a very basic observation, something so normal we barely notice it anymore. I want you to just think about this for a second. If a pen slips out of your hand, or you toss a cricket ball up in the air, it always comes back down, right? An apple from a tree. It always falls to the ground. Why? What is this invisible pull that brings everything down towards the earth? And the answer, as you probably know, is the force of gravity. Our planet Earth, because it's so massive, pulls every single thing towards its center. It's this continuous, invisible force that keeps us on the ground and makes everything fall. Okay, so we know things fall because of gravity. But, in physics, we like to be very precise. So we have a special name for this specific kind of motion. Let's find out what that is. And that special term is free fall. Now pay close attention to the definition here. It says, whenever objects fall towards the earth under this force alone. That word alone is the most important word here. It means we are imagining a perfect situation where only gravity is acting on the object, nothing else. No air, no friction, just gravity. That's free fall. So we have an object in free fall. But what happens to its speed as it falls? Does it stay the same? No, of course not. We know it gets faster and faster and faster. And this change in its speed, well, that brings us to our next big idea. Remember from our earlier chapters on motion? Whenever there's a change in velocity, we call it acceleration. And since a falling object's velocity is changing, it's increasing, the object must be accelerating. This special acceleration, caused only by the Earth's gravity, gets a special name. We call it the acceleration due to gravity, and we give it the symbol g. So let's get to know our new friend g a little better. What are its properties? First, its symbol is a lowercase g. Simple enough. And its direction? Well, since gravity always pulls things down, the direction of g is always towards the center of the Earth. And finally, because it is an acceleration, its SI unit is meters per second squared. Now, I'm sure you have heard your teachers mention the number 9.8. But where does this number actually come from? How did scientists figure out this value? It's not just a random number. There's a beautiful calculation behind it. Let's see how it's done. This is where it gets really clever. We look at the force on a falling object in two different ways. First, using the universal law of gravitation, we know the force is F equals g times mm by r squared. But we also know from Newton's second law that force equals mass times acceleration, which in this case is F equals m times g. Now, both of these are describing the exact same force, so we can put them equal to each other. And when we do that, something amazing happens. The mass of the falling object, the small m, is on both sides of the equation, so it just cancels out. And what does that mean? This is a huge conclusion. It means that the acceleration of a falling object does not depend on its mass at all. It doesn't matter if it's a heavy cricket ball or a light tennis ball. In the absence of other forces, they will accelerate at the exact same rate. Just let that sink in for a moment. It's quite profound. So, once the mass of the object is gone from our equation, we are left with a formula for g. And if we put in the known values for the universal gravitational constant, the mass of the Earth, and the radius of the Earth, what number do we get? You guessed it. We get 9.8 meters per second squared. And that is where that famous number comes from. Now here's a little extra detail for you. The Earth is not a perfect ball. It's slightly flattened at the poles and it bulges a little at the equator. This means you are slightly closer to the center of the Earth if you are at the poles. And because of this, the value of g is slightly, just slightly greater at the poles than at the equator. But for all our problems in class, taking g as 9.8 is perfectly fine. So, we have just proved that all objects should fall at the same rate, right? But hold on a minute. Is that what we actually see in our daily lives? If you drop a big stone and a little feather, do they really hit the ground together? Let's investigate this real-world puzzle. Let's try a small experiment in our minds. In one hand, you have a stone. In the other, a flat sheet of paper. Now, imagine you drop them both at the same time from the same height. Which one hits the ground first? The stone, of course, every time. But this seems to completely contradict what we just learned. So what is going on here?
The secret lies in a force that we decided to ignore earlier to keep things simple. And that force is air resistance. See, as an object falls, it has to push through the air, and the air pushes back on it. This push from the air is a type of friction that slows the object down.
Now let's compare. In real life, with air, that big flat sheet of paper catches a lot of air. It acts like a tiny parachute, so air resistance has a big effect and slows it down a lot. The small, dense stone just cuts through the air easily. But what if we could remove all the air? What if we did the experiment in a vacuum? Well, in that case, with no air resistance, the paper and the stone would fall together, side by side, and land at the very same instant. And this isn't just a thought experiment. There is a famous story about the great scientist Galileo. It is said that he went to the top of the Leaning Tower of Pisa and dropped two cannonballs of different masses. And, to everyone's surprise, they both landed at almost the exact same time, proving his point that gravity pulls on all objects equally. Phew! We have covered quite a lot of ground today, haven't we? So let's just pause for a moment and go over the main points, the things that you absolutely must remember from this lesson. So let's do a quick summary. First, what is free fall? It's when an object falls with only gravity acting on it. Got it. Second, this fall causes an acceleration g, which we call the acceleration due to gravity. Its value is 9.8 meters per second squared. Check. Third, and this is a big one, the value of g does not depend on the object's mass. Check. And finally, why do things look different in the real world? Because of air resistance. Check. If you remember these points, you have understood the core of today's lesson. So today, we've built a really strong conceptual foundation. We understand what free fall is and what g is. But this is just the start. The really fun part is using this knowledge. So the question for next time is, how can we use this value of g to solve actual problems? Like, how can we calculate how fast an object is falling or the height of a tower? That is what we will explore in our next session. So stay curious, and I will see you then. Thank you.